Welcome to class number 3. Have a seat. You will have your homework posted on Blackboard this evening. And just as an announcement, it shouldn't be necessary because every week you will have, you should check the announcements for any change in schedule. But in general, we will have always a homework posted on Wednesday evenings, unless otherwise noted, okay? So let's start this third lecture with a little riddle of nature in this video that I want you to watch. No audio, I've turned it off because there's no need. Just watch. Okay, so anyone, have you seen this video before? Anyone? No? You have? Okay, you're ahead of the rest of us. You might know the explanation then. I'll ask you to have a little patience to challenge everyone else in the class to think a little bit about what you just saw. And can you come up with an explanation of what is going on there? Anyone? Any ideas? The magic word was pronounced in the back of the room, surface tension. You knew that? No? So you didn't know the explanation. Okay, you just watched the video. Good. Surface tension. This is what we're going to be talking about this lecture. The property of surface tension. Do you have any idea how surface tension causes what we just saw? Let me see if we can just pull it back a little bit to the important part. That's very interesting, isn't it? Okay, so first of all, we have sprinkles of pepper in the surface of the water, and well, they don't sink is the first observation. They just sort of float, okay? And they stay in one position on the surface. They don't really move until you do anything about it. Basically, the water is pulling each grain of pepper in every direction in equal manner, so the pepper grains are not moving. As soon as you put a little drop of soap, which is a compound that is able to change the surface tension of water, you have a localized area there where the water somehow is pulling the pepper grains less than everywhere else. And so the pepper grains are pulled towards the edge of the dish here, where the surface tension is higher. So basically the grains are being pulled to the edge when you decrease the surface tension in that little spot in the middle. Does that make sense? Intuitively first, we haven't defined surface tension or discussed it more a little bit in terms of the physics, but that is sort of the explanation in terms of the inside of what's going on. So when the detergent comes in contact with the water, basically it reduces its sort of like quote unquote pulling action on the pepper grains. Okay? So here is a picture of a feather. If you take a feather, a natural feather, and you dip it into water, you will observe, suppose that I'm dipping it in a glass of water. What you will see is like a silvery lining on the feather, because as you dip it in the water, basically there's a layer of air that stays there on the surface of the feather. The reason for this is that birds have what's called a preening oil that covers all of their feathers. And so if you take a natural feather and you dip it into water, basically the water is not really wetting all of the feather. Now, if you take the feather and you say, spill a little bit of, say, cooking oil, you can do this experiment at home, and put a little cooking oil on the feather, and then you dip it again in water, you will see that there is no silvery lining anymore on that feather. You won't see that. The water actually, what happens is the oil in the water mixes with the bird's natural oils in this case, because the oil, if you, I think I said that wrong, so put the oil in the water rather than the feather. Put the oil in the water, and then you dip it, and then the oil in the water mixes with the preening oil on the feather, and it doesn't entrap that air any longer. So in nature, when a bird is caught in an oil spill, and now I've just remembered that due to the fact that I got home late from my train ride last night, I don't have the nice high impact picture I was going to grab from the internet of a bird covered in oil. So forgive me, you've seen plenty of those on the news. Imagine that there's a poor pelican there that is covered in oil, because that was my intent. Okay, so what happens when a bird is covered in oil from an oil spill? Basically, that oil and the oil from the water allows the water to wet the feathers all the way. And what happens is basically the bird doesn't have a layer of air any longer to act as an insulator for the cold. And they just die of cold many times. They freeze. They don't freeze as in zero temperature. They just get cold and hypothermia and they die. So what do the rescuers do? Suppose they grab the bird and they wash it in detergent. Suppose you grab the little feather and you wash it in detergent and you dip it as an experiment in a glass of water. What will you see? Well, there won't be any silver lining. Basically, you've washed out all the oils, even the natural oils, and so there won't be any air entrained, and the water is able to wet the surface completely. So what happens in a rescue situation is that you have to wait for after they wash the birds, you have to wait for the birds to actually cover themselves again in that natural oil before they're released into nature again. So you can imagine that it's a long process for that reason. That is what happens. The birds actually can die of cold because they no longer have that natural layer of oil. What is that oil doing there? And what is the effect of surface tension? That's what we're going to discuss today. This picture, fortunately, I already had in my computer so that I could include in my presentation today while I prepared in the train. This is a very interesting bird, the phalarope, and there are several varieties, and they have very thin, long beaks. And they feed in little small crustaceans that are sort of suspended in the water. They have very strange and interesting feeding habits that haven't been explained until very recently. So let me show you a video of what these birds do when they feed. Watch this, on the left. And here a close-up in the right. Good question. I think they twirl in every which direction. They probably alternate so that they won't get dizzy. So they have several shorebirds have these very thin, long beaks, and for a long time, people were quite intrigued about how the food managed to actually get from the tip of their long beak into the mouth. And as you see there, the bird is sort of plucking on the water, so it's very strange behavior. So how do you can imagine that they sort of grab a little bit of water in the tip of their beaks. How do those drops of water somehow get to their mouth? That's the question. Suction cannot be used to explain this. It's not like a straw because the geometry is an open geometry. The beak is not closed like a straw. So they can't really use suction. That's not an explanation. So how do they manage these things? To explain this, and I promise to you at the end of the class you will fully understand what's going on, we need to understand surface tension. So, here is a little close-up of the beak and a little drop of water caught there. By the end of the class today, we will understand how that little drop of water manages to go to this bird's mouth for it to feed. Surface tension. It's an attractive property of the surface of the fluid. So if you look at this picture on the side, and you can try to draw an equivalent on your notes, what you have is, a surface, and if I take a zoom in to the molecular level, I can imagine that there are lots of molecules at the surface, and the molecules at the surface are pulled by the cohesive forces of other molecules. But the molecules inside the bulk of the fluid are pulled in every direction equally, while the molecules at the surface are basically only pulled from the bulk, from the inside. So the effect, the total effect, just in sort of a physical, insightful explanation, is that there's an imbalance of molecular cohesive forces. And basically, the molecules in the bulk of the fluid are surrounded everywhere by other molecules, and so feel an equal pull in every direction, sort of like perhaps those granules of pepper that you saw. But when there is an imbalance of that pulling action of the molecules, then there's going to be a total force. And in this case, the molecules along the surface are subject to a net force which pulls them towards the interior. And the result is a sort of tension. So this can be considered as a tensile force. in the plane of the surface, of the interface. The interface between the liquid and the gas phases. Our formal definition for surface tension is that it's a force along the line of unit length parallel to the surface. So it's force per unit length. Force along a line of unit length parallel to the surface. So the dimensions, usually we use the Greek letter sigma, lowercase sigma, for surface tension. Sometimes other sources will have lowercase gamma. But since we use gamma a lot for this specific weight of fluids, we'll just use sigma for surface tension. And the dimensions, I said, is a force of unit length. So force divided by per unit length, or force divided by L, length, and the units then in our metric system are going to be Newton per meter, and in the British gravitational system are going to be pounds force divided by feet. So the trick is to remember that this is a force per unit length on a line that is parallel to the surface. So immediately let's do an example so that this becomes clear. Before my example, of course, I have a little picture for you to observe here. This is a very nice illustration of a floating paperclip. Of course, a paperclip is made of steel. Steel is heavier than water. Normally, any object which is made of steel will just sink, but here you have the effect of surface tension, making that paperclip float. So let's do let's sort of look at that picture here in an example calculation. See, I did this very late last night. I don't even remember that I've added all these little quirky examples. The floating razor blade, again made of steel, stainless steel. It should. This one doesn't float, I think. Yeah. Okay, so here's the example finally. So imagine we have, well, like the case of the paperclip, okay, a solid cylindrical needle of diameter D and length L. So it's diameter D and length L. And the length is quite long, it's not said, but we imagine the paperclip situation, but we're just looking at one long cylinder. And the diameter is D, length is L, and the density of that material, say it could be steel, is rho A. And we're saying this is floating on a liquid surface just like the paperclip we've shown before. And the question is, calculate the maximum diameter for the needle to be able to float on the surface. So thinking about that paperclip situation that we just seen on the picture, let's just look at sort of a zoom in of a cross section of the paperclip, and we have the cylinder here, and you saw that sort of the surface of the water bends like this, and we have the force of surface tension acting on either side. Here I've drawn a cross section of the cylindrical needle, like that. So what is surface tension? We said surface tension is a force per unit length. And so to obtain the force, we need to, well, multiply by the length to get force, right? So surface tension, sigma, is force per unit length. I multiply by the length and I get the force. So we have here acting on each side sigma L and sigma L. Of course, surface tension is acting all along that line of contact between the cylindrical needle and the surface of the fluid. And so now we can make a very simple free body diagram of this situation, because obviously there's the weight acting downwards and the surface tension acting upwards. And so surface tension, we see, is it provides an upward force, which balances the weight of the needle. So the total forces must be zero because the needle is stationary there, floating, and we have we're ignoring, of course, so I'm taking just the length on both sides of the needle, and I'm ignoring that little surface which is across the diameter, which is also at play, but I'm taking it to be much smaller than the whole length, and so I'm just taking sigma L and sigma L, okay? Do you see that? Okay. So the total force is, well, it's acting on both sides, so we have 2 sigma L, the surface tension, and the weight, we're giving the density, so density times volume times the acceleration of gravity. The volume is pi/4 d squared times L, and if we multiply by g, we have the weight of the needle, and that has to be equal to 0. Now you can see that everything here is known except for d, which is what we need to solve for, the diameter, such that this whole thing is in equilibrium, and the needle floats. We're ignoring effects of, say, buoyancy. Okay, we haven't discussed buoyancy yet, but we're ignoring those effects. Consider this to be unimportant. But just to be clear, we write it down there. And so we solve now for d. And, well, I'm going to have a square root, and I put everything on the other side. I have 4 times 2, that's going to be the 8 here. Sigma L cancels out, interestingly enough. And we have pi rho g. So now we could sort of try out some values and see what this comes out to. So suppose we try out steel. We look up the properties of steel, and we have for steel that the specific gravity is equal to 7.84. That means it's 7.84 times as heavy as water. Rho g is equal to its specific gravity, and this is in water at 20 degrees. We've looked up this in some table in the back of the book or somewhere else, and so we obtain for the case of steel that we can put all of the numbers in, and notice that this has no units, no dimensions, it's specific gravity, and normally we would want to write out all of the units, but I'm going to just skip that part and leave it to you to check and give you the answer. It's 1.6 millimeters. So if you have a chance later when you're reviewing material, do carry all your units and check that it's correct. Yes?
So that's specific gravity? What's that?
So we know the,
So that would be put in for...
this is rho of the fluid and, of the steel here. And we know the density of water, and so we would we'd have to look this up too. I didn't write it down, I'm afraid. So we would need the surface tension from a table. I've been sloppy here in preparing the example for you, but you need the surface tension and the density of water and acceleration of gravity. So all of these things are known in this situation. Yes?
It's always based on the submerged length.
On the what?
On the partially submerged, the length in contact.
In contact, yes. We could, in this problem, be a little more, rigorous. We could have considered the diameter. I mean, I'm sort of considering that it's right at the length, and this surface on this face doesn't really matter. I'm considering this to point upwards. I haven't thought about any situation of angles. But if it was pointing in an angle, you can see that the horizontal components would cancel out. So anyway, the vertical component is what matters. I haven't said anything about the angle here of contact yet, but we'll discuss it a little bit later in the class today. Yes?
The density, is that the density?
This guy is the density of the needle because this is the weight of the needle.
Oh.
So, but by giving you the specific gravity here, you would have to put rho A is equal to specific gravity times the rho of the water. And so now,
In the case of that razor blade floating on the surface, is there an area for the length?
no, it's always the length. So suppose that we have the razor blade. Then we would have to count, if razor blade is lying flat, we would have to count the following length. This, plus this, plus this, plus this. All of the contact line. All along that line, and this is the only trick about this concept, is that it is a force per unit length, and it's acting along a line. Imagine that basically you were pulling on the contact line. The water is pulling on the material on the contact line, and that's the tension that is holding it. Like when you're holding a trampoline, all around it, the trampoline has, this. It's attached to a frame, and that frame is pulling it, and that tension keeps up whatever weight is put on that. Is the outer edges that matter, exactly. Just like a trampoline. Imagine the trampoline, and that should give you the idea. In the trampoline, all the forces are being applied on the frame, really, and that holds all the weight because it's a tension force. And so this would be the frame of the trampoline for the case of a razor blade. Does that make sense? Yes. Yes, indeed, sir. We will see that is one of the important factors in surface tension. Yes. I couldn't hear you. I'm sorry, because of the air conditioning. We normally would have for the 4 different edges, but I have neglected the diameter because if I put it in here, it would make it a little bit more difficult for me to solve for diameter. But I've just taken this to be like a very long needle where that is really negligible in comparison to the length. That's the assumption I've taken to be the D much smaller than L, so I can neglect that contribution. Okay? Does that make sense now? Everybody happy? Good. So the trick is to remember that the surface tension is acting along a line where the contact with the fluid can be seen. If you've got that clear in your physical insight of the problem, then you're in good shape. Okay? So let's look at a second example. So consider that we have a drop of water momentarily floating in the air for a snapshot in time. We're looking at it, and the question is, calculate the pressure difference between the inside of the drop and the surrounding air. And I'll just give you a minute to take note of that question. On your notes for your reference. So in my sketch there, I have drawn actually just half of the drop. Okay, so I'm going to look at one half of the drop to be able to flesh out the effect of surface tension on the drop. And we're going to do a free body diagram of that half drop. Of course, the other half is going to have exactly the same situation, and the surface tension is sort of keeping the two halves together, right? So we're going to do a free body diagram, which I've already pictured here. Of one half of the drop. Inside the drop, we have a pressure, P, which is the unknown. And all along this interface, we have the action of surface tension. So we have sigma acting all along this line on the interface for this half drop. So what we have for the force due to surface tension is, well, the line along which surface tension is acting is just the circumference here. So 2 pi r. We haven't written here the droplet of water in air radius r. We need to assume a size. 2 pi r is the circumference, and multiplied by the surface tension gives me the force. Force times length, surface tension times length gives me the force. This force needs to be balanced by a pressure inside of the drop. I've drawn here this force due to pressure as this big green line here. It is a pressure difference between the inside and the outside of the drop. And we balance these forces, and so we have that 2 pi r sigma has to be equal to the force due to pressure. Pressure is force per unit area, and so we have to multiply by the area to get a force. So we have pressure times the area where that pressure is acting is where we've cut the drop in half, so pi r squared. Delta P is what I called it, really. The difference between the pressure inside and outside. Everybody with me there? Yes? Good. So now, obviously, we can solve for delta P quite easily, and we get this delta P is basically the pressure inside minus the pressure outside, and that is equal to, one of the r cancels out, and we have 2 sigma. The pi also cancels out, 2 sigma over r. So a couple of things that you can conclude from this. First, you can see that the pressure inside the drop is actually larger than the atmospheric pressure. And the other thing that you can see from this equation is that if r is small, then, for the case of small drops, then the pressure difference is going to be large. So for smaller drops, there's a larger pressure inside. And that is going to produce very interesting physics for drops. We're going to use this result further on as well today, later in the class. Everyone happy with that up to here? Yes. So this is inside and this is outside. So it's acting inside, so this P is acting inside, and of course ambient pressure is acting everywhere equally. So the difference in pressure is what balances the surface tension force to keep the shape, to keep the drop together, right? To keep it as a one volume. Okay. So in the case of a situation where surface tension dominates, suppose that we could have effects of gravity, but effects of gravity, are going to be sort of in competition with surface tension in a true situation. But to be able to look at the effects of surface tension alone, we want to extract other effects and imagine that surface tension dominates. Okay, in that situation, the interfaces normally evolve to minimize the area. Now, in an experiment, if we would like to remove the effect of gravity to observe that situation, one possibility is to use 2 fluids that cannot mix but have the equal density. So in this experiment that I'm going to show, is this a little video here, what we have is a pool of water with salt. The salt is stratified, so basically it's denser at the bottom, less dense, less dense, less dense as as the ocean. So we have stratified salt water. And in the video you're going to see some drops of colored oil. With basically an intermediate value of density. So the liquid has more salt at the bottom, so it's denser there, less salt at the top, so it's in the top you can put sort of clear, fresh water, and that will result in a stratified fluid. And at some intermediate value of the density, you pick an oil material that doesn't mix with the water, and that's the fluid that is going to be used to drop some, to put some drops in there. Let's watch it. And you can see that in this situation we obtain perfectly spherical drops. And the reason is that in a sort of enclosed volume of fluid, for a fixed volume of fluid, the minimal area is a sphere. Do you understand the experiment that I've described here? Yes? Good. Now, another possibility is, you don't have, here's another possibility, is a soap film between two rings. And look at the surface. Let me put it back here and pause it. Oh, before that. The surface that soap film acquires is a surface that minimizes, in that case, the so let me just point out that this is a minimal surface subject to some constraints, and the constraints is that the top and the bottom is attached to those two rings. That is a constraint, and then we have, this is another minimal surface subject to that constraint. In this situation, what we have is that there's the same pressure. So basically we had, for the drop, we had delta P equals 2 sigma over L, R, 2 sigma over R, that's right. For this situation here, what we have is delta P equals sigma 1 over R1 plus 1 over R2, where R1 and R2 are the curvatures of two perpendicular planes. So one plane would be a plane parallel to the rings, and in that plane what you have, if you're looking from above, is just a circle. So you have positive curvature, and in a plane parallel to the screen here, we have negative curvature, and so these results in a zero pressure difference in this case, because there's atmospheric pressure on both sides of this soap film. So that's the case for general surfaces. Like that. And this surface that is adopted here by the soap film is what's called a catenoid. You see those sorts of surfaces in other fields as well of engineering. Okay, so let's take a break here a little bit and then come back to this interface question and surface tension.